In this lesson, we will discuss a special type of function called a homomorphism. Homomorphisms are central to all aspects of abstract algebra. A homomorphism is a function or a mapping from one algebraic system, like a group, for example, to another like algebraic system. And this mapping preserves the structures of the domain and the codomain. So let's begin with a precise definition of a homomorphism for groups. Let G and H be groups then a map or function, let's call it phi, that maps from G to H. So G is called the domain, H is called the codomain. This map is called a homomorphism, if phi of x times y equals phi of x times phi of y for all elements x, y in the domain G. So this homomorphism takes elements of G, maps them to elements of H in such a way that the group operation is preserved. And so the structure of the two sets is preserved as well. Now some notes about this equation. Notice that this product, x times y, is a product that's taking place in the set G. So phi is mapping the product x times y and G to phi of x times phi of y, and phi of x is an element of H, phi of y is an element of H, so the product on the right is actually taking place in H. So the product xy on the left takes place in G, while the product on the right, that is the product phi of x times phi of y, this product takes place in H. So let's give an example of a homomorphism from two groups. Let's let G be the group of real numbers under addition, and let H be the group of non-zero real numbers under multiplication. So both of these are groups, and we're going to define a homomorphism from G to H. Define phi from G to H by phi of A equals 2 to the power A. So we take any real number A and raise 2 to the power A. And this is a homomorphism. Let's verify that. So to verify that phi is actually a homomorphism, we must check that now we said that we need to check that for any elements x and y in the domain, phi of x times y equals phi of x times phi of y. But the group operation on G is addition. So instead of writing phi of x times y, for example, I'm going to write phi of x plus y. Okay, so that's the group operation in G, addition. We need to show that phi of x plus y equals phi of x times phi of y, because the group operation in H is multiplication. We need to check this for all x and y in G. Well, let's look at phi of x plus y. Phi of x plus y is 2 to the power x plus y, but by properties of exponents, I can rewrite 2 to the power x plus y as 2 to the x times 2 to the y, and that is equal to phi of x times phi of y. Thus, phi is a homomorphism. Next, we will explore the notion of when two groups are essentially the same. So this means these two groups have the same group structure. So we'll describe this more precisely in a minute, but let's give an example first of two groups that are essentially the same. So consider the group it's called G, and it has three elements, an identity and then two other elements, A and B, with Cayley table Okay, this is the Cayley table. It's a group under multiplication. So we have multiplication, 1, A, and B are the elements. So the first row, 1 times 1 is 1, 1 times A is A, 1 times B is B, A times 1 is A, B times 1 is B. Now A times A will give me B. A times B will equal the identity. In the last row, B times A will give the identity, and B times B will give A. So this is the group table for this group G. So we have all the products, all the possible products listed here. Now consider the subgroup of the symmetric group of degree 3. It's called H, and this set contains the identity permutation. It contains the 2-3 cycles as well. So the cycle 1, 2, 3, and the cycle 1, 3, 2. Okay, so this is actually a subgroup of S3. Then let's look at the Cayley table for H. So this is a group with operation composition. Okay, so in the first row, 1 composed with 1 is 1. The identity permutation composed with any other permutation is just that, equal to that permutation. So this is just 1, the cycle 1, 2, 3, the cycle 1, 3, 2. Then composition of 1, 2, 3 with 1 would again just be 1, 2, 3, and 132 composed with the identity is 132. Let's do the non-trivial compositions. So let's compose 1, 2, and 3 with itself. Well, if we consider the permutation 1, 2, 3 on the top row first, it maps 1 to 2. So 1 gets mapped to 2, and then this permutation on the left sends 2 to 3. So in the composition, 1 gets sent to 3. By the same steps, we see that 3 gets mapped to 1, and 1 gets mapped to 2 under the composition, so 3 gets sent to 2. So the composition of 1, 2, 3 and 1, 2, 3 is the permutation 1, 3, 2. Since this is a Cayley table and we haven't used the identity permutation yet in this row, we know that it must be the identity. But you can do the composition. You see that 1 gets mapped to 3, then 3 gets mapped to 1, so 1 is fixed. 2 gets mapped to 1, then 1 gets mapped to 2, so 2 is fixed, and 3 gets mapped to 2, and then 2 gets mapped to 3, so this is the identity permutation. In the bottom row, let's compose 1, 3, 2 with 1, 2, 3. So 1 gets sent to 2, and then 2 gets sent to 1. So we see that 1 is fixed. Similarly, 2 is fixed because 2 gets sent to 3, and then 3 gets sent to 2, and 3 is fixed. 3 gets sent to 1, and then 1 gets sent to 3. So we see that 1, 3, 2 composed with 1, 2, 3 is the identity permutation. And then finally, 1, 3, 2 composed with itself maps 1 to 3, and then 3 to 2. So in the composition, 1 gets sent to 2, and then 2 gets mapped to 1, 1 gets mapped to 3, so 2 gets mapped to 3 in the composition. So this finishes the Cayley table for this subgroup H. Now let's look at these two Cayley tables of the groups G and group H. Essentially, they're identical Cayley tables. The only difference is the name of the operation. We have multiplication and composition, and then the actual names of the elements. Up to labeling the elements of these two groups, these are really essentially the same exact group. So notice that these two tables have identical structures. The two tables would actually be identical if we simply relabeled the elements of, let's say, the Cayley table of H. So if we called the permutation 1, 2, 3, if we called this A, and we called the permutation 1, 3, 2 B, then we'd see that these two Cayley tables are exactly identical. So when two groups are the same except that their elements are labeled differently, we call them isomorphic. So in this case, G and H are isomorphic. So we'll describe this precisely in a minute, but essentially when two groups are isomorphic, that means their group structures are exactly the same, and the only difference really is a labeling of the elements. So let's be more precise with our definition of isomorphic. First, we need to define an isomorphism, which is a special type of homomorphism. So a homomorphism phi from groups G to H. This homomorphism is called an isomorphism, and G and H are isomorphic, and we write G is isomorphic to H as G and then an equal sign with a tilde above it. So this is red. G is isomorphic to H, or G and H are isomorphic. So this occurs. So phi is not only a homomorphism, but phi is a bijection, that is a one-to-one and onto function from G to H. So if phi is a bijection, so that is a function that's one-to-one and onto. So to show that two groups are isomorphic, we often define a homomorphism. We define a function phi. We have to show that it's a homomorphism first, and then show that it's also one-to-one and onto. And if such an isomorphism exists, then we say G and H are isomorphic. So we said that two groups are isomorphic if they're essentially the same up to the labeling of the elements. So we can think of an isomorphism as a way to kind of translate or interpret one labeling to another. So you take an element of G, the isomorphism maps that element to an element of H, and it kind of matches up the two elements in a one-to-one correspondence. So we can kind of translate the different labelings of the groups. So in summary, two groups G and H are isomorphic if there's a bijection phi between them that preserves the group operations. A quick example of an isomorphism: for any group G, it's clear that G is isomorphic to itself, and we need an isomorphism. Well, the identity map let's call it phi from G to G, and phi maps any element of G to itself. This is clearly an isomorphism. So G is isomorphic to itself. We gave an example earlier of a homomorphism from the real numbers to the non-zero real numbers. While this homomorphism was not an isomorphism, we can fix it. We can say that, for example, the same map phi of A equals to 2 to the power A. It's a homomorphism. We showed that earlier, but this is actually an isomorphism from the real numbers under addition to Now, this function does not map onto all non-zero real numbers, but it does map onto the positive real numbers. So this is an isomorphism from the real numbers under addition to the positive real numbers under multiplication. So we showed already that phi is a homomorphism and phi actually has an inverse function since phi is an exponential function. The inverse, phi inverse, is a logarithmic function. So the phi has an inverse defined by phi inverse of x is the log base 2 of x. So we have a homomorphism that has an inverse, therefore phi is a bijection any function with an inverse will have to be one-to-one and onto. Therefore, phi is an isomorphism from the reals under addition to the positive reals under multiplication. Next, let's look at an example of two groups that are not isomorphic. So let n and m be positive integers, where n and m are not equal. Then let's look at the symmetric groups. Well, we know that the Sn, symmetric group of order n, has n factorial permutations. There's n factorial permutations in Sn, so the order of Sn is n factorial. Well, if n does not equal m, then this will not equal m factorial, which is the order of Sm. Sm has m factorial permutations. So if you have two groups that don't have the same size, the same order, there's no way you can define a one-to-one onto function from Sn to Sm. So there is no bijection from Sn to Sm. Thus, if m does not equal n, Sm and Sn are not isomorphic. So in general, two groups are not isomorphic if they have different group structures. One big structure of a group is the actual number of elements inside that group. So two groups that have different orders cannot be isomorphic. So two groups with different orders are not isomorphic. So this is one of the facts that we will actually prove in the next theorem. So in this theorem, let's suppose we have an isomorphism from two groups G to H. So if phi maps from G to H, and this is an isomorphism, then by definition, G is isomorphic to H, and we have the following facts. First of all, phi maps the identity element of G, let's call it 1G, so this is the identity of G. Any isomorphism will map the identity element of G to the identity element of H. Let's call it 1 sub H. Okay, so under any isomorphism, the identity of G gets mapped to the identity of H. Secondly, G is abelian if and only if H is abelian. So abelian is a group structure that has to be preserved in order for two groups to be isomorphic. The third fact, given any element of G, the order of X, so this is as an element in G, will be equal to the order of its image, so the order of phi of X in H. So X and phi of X have the same order. And finally, the order of group G has to be equal to the order of group H. And the proof essentially of the last statement is the fact that you can't have a one-to-one correspondence of elements in G and H if one has more elements than the other. Let's begin the proof. Well, for part A, let's take phi of the identity element of G. The identity element of G times itself is the identity, so this is the same as phi of 1 times 1. And then, since phi is a homomorphism, this is the same as phi of 1 times phi of 1. Now, phi of 1 is an element of H. So since phi of the identity of G is an element of H, when I multiply it times the identity element of H, it's unchanged. So phi of 1 equals 1, the identity element of H, times phi of 1. Then by combining these two equations, we see that 1 times phi of 1 equals phi of 1 times phi of 1. But then we can cancel phi of 1 on the right. So by cancellation, we have that the identity element of H equals phi of the identity element of G. So that establishes part A of this theorem. Let's look at the proof of B, the fact that G is abelian if and only if H is abelian. Well, if G is abelian, by definition, that means that A times B equals B times A for all A and B in G. By applying the isomorphism phi, we see that phi of AB will equal phi of BA for all A and B. But this is true if and only if phi of A times phi of B equals phi of B times phi of A by the properties of a homomorphism. And since A and B are arbitrary, phi of A and phi of B are arbitrary elements of H. So this is true for all phi of A and phi of B in H. And this is the same as saying that arbitrary elements of H commute. So H is abelian. So we see that two groups that are isomorphic must either both be abelian or both be non-abelian. So there's no way you can have an abelian group be isomorphic to a non-abelian group, which could be a useful way to prove that two sets are not isomorphic. If you could show one group is abelian and one group is non-abelian, then there's no way they can be isomorphic. Now for the proof of part C. Let X be an element of G, and suppose phi of X has order n. So by definition of order, then we know that phi of X to the power n is the identity in H, but further, n is the smallest positive integer that satisfies this equation. So we know that phi of X to the power m does not equal the identity when m is between 1 and n. So for all integers m between 1 and n. Okay. Now let's look at phi of x to the n. Phi of x to the n, well, x to the n is x times itself, total of n times. And by applying the definition of a homomorphism over and over and over, we see that this just equals phi of x times phi of x times phi of x n times. So this is phi of x to the power n. But n is the order of phi of x, so this just equals the identity. Now we're going to use statement A. So consider part A of this theorem, which states that the identity element of G gets mapped to the identity element of H. But we just showed that phi of x to the n equals the identity element of H. So therefore, by part A, x to the n must be equal to the identity element of G. Again, this is since phi of x to the n is the identity element of H. So this shows that the order of x cannot be bigger than n, because we just demonstrated that x to the power n is the identity. So then the order of x is less than or equal to n. So it remains to show that the order of x can't be smaller than n and must be equal to n. So suppose x to the m is actually equal to the identity in G for some smaller power of x. Let's say for some integer m between 1 and n. Well then, phi of x to the power m would similarly equal phi of x to the m by the properties of a homomorphism, and x to the m is the identity element in G, and we know that by part A again, phi of 1 equals 1. This would show that the order of phi of x is less than n, which is a contradiction. Thus, the order of x can't be smaller than n, and we conclude that the order of x equals n. So part C is an interesting statement. It says that if the order of x in G must be the same as the order of its image, phi of x, in H, if G and H are isomorphic. So for the proof of D, think about the following conclusion from statement C. By part C, we can deduce that groups G and H have the same number of elements of any given order. So let's say of order n for all natural numbers n. So that is all positive integers n. Because any element in G would have the same order as its image in H. So for any positive integer n, G and H have the same number of elements of order n. So then overall, if you consider all the possible orders, G and H must have the same number of elements. So thus, G and H must have the same number of elements in all. Since phi puts G and H in a one-to-one correspondence, we see that G and H must have the same number of elements. And this concludes the proof of the theorem.